It's my great pleasure to present Reid that will talk about distinguishing certain triangle groups by the finite quotients. Please.
Obrigado. Primeiro, gostaria de agradecer pelo convite de falar aqui na UNB. É uma pena que não posso estar aí em Brasília. Próxima vez, eu espero. Mas agora eu vou continuar em inglês. Meu português não é tão consistente. Desculpe. Okay. So what I'm going to talk about is joint work with Martin Breitson and Ben McReynolds and Ryan Spittler. Some of you have at least heard some of our work before, possibly even this work before. But anyway, this is part of an ongoing program, particularly with Martin, where we're trying to distinguish certain groups by their finite quotients. So let me get started. So standing assumption throughout the talk is that all the groups are finitely generated and residually finite. So residually finite, recall, means if you've got a group gamma, let's just say finitely generated, even though it doesn't have to be, and gamma is a non-trivial element in gamma, then we can find a homomorphism from gamma to some finite group Q for which phi of gamma is not the identity. So we can do this for all non-trivial elements. We can find a finite quotient that doesn't kill gamma. So in particular, the point about residually finite groups is that they've got lots of finite quotients. And if we're trying to kind of distinguish groups by their finite quotients, we better have a rich supply of finite quotients for which to work with. So, you know, there are many examples. So examples. We could take finitely generated subgroups of GLNC. And then it's a theorem of Maltsev that they're residually finite. And then another class of examples is the fundamental groups of compact three manifolds. So this is a consequence of Perlman's solution to geometrization, together with an old argument of John Hempel and Bill Thurston. So there's a rich supply of groups that have this residual finiteness property. Now, there are groups that are not residually finite, but they don't tend to live in my office. So I tend only to think about things that are residually finite. So let me introduce some notation here. So the broad brush is, you know, we're going to look at this finitely generated residually finite group. And we're going to ask the question, you know, to what extent does this collection of finite quotients determine gamma? So C gamma here is just the set of finite quotients of gamma. Okay, and maybe we put here square brackets just to emphasize that we should think of isomorphism classes of finite groups. So the point is that, you know, if the alternating group on 17 letters occurs as a quotient of gamma, it goes in the list. I don't care if it occurs in 17 different ways. It just goes in the list because it's a finite quotient. So there's no other further information about this set. It's just a set of finite quotients. And the question that I'd like to talk about is to what extent does this set determine the group gamma up to isomorphism? So I like to think of this question as a local to global question. There's many parts of mathematics for which local to global questions are interesting, and this seems to be another particular example of this. And how might one think of this as a local to global? Well, if we fix a finite set of generators for the group gamma, then we can build its Cayley graph with respect to that finite collection of generators. But then we have all of these finite quotients, and because we're residually finite, if we take a big ball in the Cayley graph for gamma, we can embed that ball in a large finite quotient of gamma. And in particular, we take the Cayley graphs with respect to the finite quotient, so we see this big ball of the Cayley graph in the infinite group embedding in the Cayley graph of some of the finite quotients of gamma. So the local objects are really these finite Cayley graphs, or the balls in the finite Cayley graphs. And the question is to what extent they can be reconstituted to give us the global Cayley graph. And so that's kind of how I like to think often of this particular question, the local data being the finite Cayley graphs and the global data being the global Cayley graph. So I'm not going to give too many examples of groups that are determined by the finite quotients and groups that are not determined by finite quotient. There's been a lot of work on this over the many, many years, but I'll just maybe mention a few examples, maybe two basic examples, and get to the context that Martin and I are kind of most interested in. So the most basic example of all is perhaps if we just take the infinite cyclic group, and we can convince ourselves very quickly that it's determined by its finite quotients. The point being that if we have lambda, so again, just for emphasis here, this finitely generated and residually finite group, if lambda's got the same finite quotients as the infinite cyclic group, well, there's two possibilities. One possibility is lambda could be non-abelian, in which case there exists a non-trivial commutator in lambda. But that's a contradiction, because by residual finiteness, this can't be killed in some finite quotient, but because all the finite quotients are finite cyclic, this must die in every finite quotient. So this is impossible. As lambda is residually finite. So secondly, lambda is therefore abelian, but then the structure theory for finitely generated abelian groups implies that lambda must simply be isomorphic to z. The point being, if there were some extra summand, suppose it was z cross z mod 17, well, we could build finite quotients that were visibly non-cyclic by using either the extra factor in the free part of the abelian group, or some part of the torsion of the abelian group. And so very quickly one has to see that lambda is isomorphic to z. So in fact, this is still true for any finitely generated abelian group. And moreover, it's also true that if we have C of gamma equal to C of lambda for arbitrary finitely generated residually finite groups, then the same kind of arguments kind of show that very easily gamma abelianized is isomorphic to lambda abelianized. Otherwise, one could find a finite abelian quotient group of one, but not gamma. Now, this is a very elementary example, but what's kind of remarkable is that one doesn't have to go very much beyond the infinite cyclic group to get examples of groups that are not determined by their finite quotients. So in fact, Baumschlag, probably many of you don't know that Baumschlag was actually a professor here at Rice many years ago in the 1970s. And it was just before he kind of went to New York. He had a student here that did a lot of nice work on the profinite, on this question for nilpotent groups, a guy called Fred Pickle. Anyway, that's a bit of historical amusement for those that know Baumschlag. But anyway, the point is here that Baumschlag built two groups, gamma 1, gamma 2, that were virtually Z. And if you chose the cyclic group in this short exact sequence that I've called F to have some property, for example, the cyclic group of order 11 works, then one could show that gamma 1 and gamma 2 were non-isomorphic, but gamma 1 and gamma 2 had the same finite quotients. So this was kind of a nice argument. So what he showed was that, you know, gamma 1 cross Z is isomorphic to gamma 2 cross Z. And this property implies that you have the same finite quotients. So, you know, Baumschlag had this goes back to Hirschhorn, this kind of stabilization by taking direct sum with Z, say. And a nice observation that these sort of short exact sequences, these extensions that were defining gamma 1 and gamma 2, the actual extension just got washed out when you cross by Z, and so they were invisible, and then you got the same finite quotient. So it's a very nice little argument, that. Okay, so no, there are, Z is determined by its finite quotients, but there are examples of virtually Z that are not. So it's kind of it's interesting that one doesn't have to go so far to get an example. Okay, so there's a huge literature on trying to prove classative groups do and are not determined by their finite quotients. The context for, you know, Martin and myself is more from the point of view of low-dimensional topology and geometric group theory. And so, you know, the most basic question that, you know, I emphasize that remains open due to Remeselnikov that was in the 70s is a question about the free groups. So we take the free group of rank n and we ask the question, suppose gamma has got the same set of finite quotients as the free group of rank n, is gamma isomorphic to the free group of rank n? And if we just sort of pause on that for a minute, we're kind of saying here that, well, let's take the free group of rank 2. We know all the finite quotients of the free group of rank 2, namely they're all finite groups that can be generated by at most 2 elements. And then what we're saying is that there's this weird group out there in the universe somewhere that, you know, it's maybe 100 generator, but all its finite quotients are 2 generator. And so, you know, the question is, does such a thing exist? So that's really been the motivating question for, you know, Martin and myself's work, and also more broadly in the context of the free group appearing in geometric group theory and low-dimensional topology. So the free group offers several nice ways to generalize this question. So the free group is the fundamental group of a compact surface with boundary. And so we could increase the class of surfaces to look at all compact surfaces with or without boundary. And so in this case, we're then really led to the question number 2 as to whether a surface group, i.e. the fundamental group of a closed, let's just say orientable surface for the sake of being specific, of genus G at least 2, the genus 1 case we can do from previous comments, is that determined by its finite quotients? And then surface groups, they can be uniformized by hyperbolic structures. And so a natural extension of this question is that we can take M to be a complete orientable hyperbolic 3-manifold of finite volume. So here we're just really thinking of M as a quotient of H3, the hyperbolic 3 space, by gamma, where gamma is a discrete subgroup, let's say torsion free, so that we get a manifold, and where there's a fundamental domain of finite volume for the action of gamma on the hyperbolic 3 space. And so the question 3 then is a natural generalization again of this. Again, the free group is the fundamental group of a closed 3-manifold, namely the connect sums of S2 cross S1s. So again, it's a natural generalization in many ways. So all of these questions remain open, but one can tweak these questions a little bit and make progress, and that's really the content of today's talk. So the free group can be realized as a Fuchsian group, and that's just a discrete subgroup of PSL2R, which is the group of orientation preserving isometries of the hyperbolic plane. And we can generalize the fundamental group of a hyperbolic manifold to just a Kleinian group, which is just a discrete subgroup of PSL2C. So let me make some comments. Again, I'm not going to go into this in too much detail, but there's been a fair amount of activity on these classes of group recently, and I'd just like to maybe comment on a couple of these. So the first thing is that in work with Martin and Marston Condor, we proved that Fuchsian groups were determined by their finite quotients amongst a more restricted class of groups, not all residually finite groups, but lattices and connected Lie groups. So if gamma is a finitely generated Fuchsian group, and lambda is a lattice in a connected Lie group with the same finite quotients as gamma, then in fact lambda is isomorphic to gamma. So lambda in fact is that Fuchsian group. So that gives a certain amount of rigidity in the setting of this class of groups. But it is still very restrictive, and it's far from proving the result that we would really want to prove. So the second case is that up in part 3 here, I mentioned fundamental groups of hyperbolic manifolds, and there's a reason for that we should maybe stick to. Hyperbolic 3 manifolds. And the reason for this is that there's work of Hempel and Funar, and also Jesus, let's spell it right, Neri, in certain cases where one shows that, in various classes of 3 manifolds, so for example, in the case of Funar and Jesus Neri, these are manifolds that are torus bundles over the circle that admit a so-called solved geometry. And in this case, one can construct many examples for which there are many fundamental groups of these manifolds with the same finite quotients. And Jesus Neri kind of proved that it's kind of related to the class number of a certain natural object associated to these bundles. So there is a reason to stick to the world of hyperbolic things, because it fails for other classes of geometric 3 manifolds. And then a piece of work that I'm particularly fond of is a result of Wilton and Pavel, that says, amongst other things, that you can recover the geometric structure of a 3 manifold from its finite quotients. So for example, let me say it like this. Suppose we've got gamma is pi1 of M3, and M3 is closed and hyperbolic, and then lambda is pi1 N3, and again N3 is just say a compact 3 manifold this time. And assume C gamma is the same as C lambda, so they have the same finite quotients, then the conjecture that we stated before would claim that gamma was isomorphic to lambda. Well, one can't prove that at the present time, but one can show quite beautifully that lambda is the n. And n is closed hyperbolic 3 manifold. So it's really kind of pretty amazing when you think about it, that you can see a hyperbolic structure just from the set of finite quotients. And it's a very, very beautiful result. So that's a geometric thing that's detected by finite quotients. And let me just mention a fourth thing. and conveniently enough is also in the audience by Andre Jaikin. And I'm going to apologize, Andre, because I'm going to spell your last name incorrectly, I'm afraid. It's like Aaron. That, let me just say it like this for those that know that fiberness of M3 is detected by C of pi 1 over n. So the property of being a fiber 3 manifold just simply means that you're a fiber bundle over the circle with fiber compact surface, or maybe in this audience, the fundamental group admits a decomposition as a short exact sequence where there's a map to Z and the kernel is a surface group, either with or without boundary. And so what Andre proved was that in the context of 3 manifold groups, this property can be seen by finite quotients, which again is kind of remarkable that one can see topology as efficiently as that. Okay, so that's just some taster of some of the work that has been ongoing. The real motivation, of course, is the 3 questions I mentioned at the start, and here's what I'm going to talk about. So I'm not going to talk about this one. Well, the last time I was in Brazil, I talked about this one at the ICM with Brightson and McReynolds and Spittler, where we constructed these Kleinian groups, so these discrete subgroups of PSL2C that were determined by their finite quotients. And again, this is absolutely amongst all finitely generated residually finite groups. So again, maybe just for emphasis, we'll sort of say here again, almost all finitely generated. Now, the downside is that even now, even though we've been working hard on this, we can still only prove that there are finitely many such hyperbolic 3 manifolds. But nevertheless, these are the first examples that one might consider as to being close to what the free group is like, in the sense of what we discussed before, that these groups do contain free groups as subgroups. And so these guys have the property of being determined by their finite quotients. So what I'm going to talk about today is another theorem that we proved, where we this time prove that there are certain Fuchsian triangle groups that are determined by their finite quotient. So recall that these triangle groups, so if we're in the hyperbolic plane and we build a triangle, then we have interior angles pi over p, pi over q, pi over r, and 1 over p plus 1 over q plus 1 over r is less than 1. And if we take the group generated by reflections in the faces, so we like delta minus pqr equal to the group generated by reflections in the edges of the triangle, then this defines a discrete group of isometries of the hyperbolic plane. Contains orientation reversing isometries because it contains reflections, but there's the so-called triangle group subgroup of index 2, delta pqr, which is presented by a and b, a to the p equals b to the q equals a b to the r is 1, that this is contained in PSL2R, and this is the triangle group. So these have been studied over the course of history of discrete groups, because they're one of the first classes of discrete groups that one could really usefully study. And what we prove in the paper is that certain of these, again, there's a word arithmetic appears in parentheses there, that's crucial as part of the construction in the same way that it was crucial in the part of the construction in the first theorem, that we're going to prove are determined by their finite quotients. Again, unfortunately, there's only finitely many. In this case, there's only 14 of these. One particular example is delta 238, the 238 triangle group. Now that may not be your favorite one, which is unfortunate. It's not my favorite one, but I can't handle my favorite one. So that, you know, we can't yet prove. So perhaps the most famous of these triangle groups is the 237 triangle group, but our methods can't deal with that as yet. And I'll maybe make a comment at the end as to what the problem is. So what I'm going to talk about is just some of the ideas that go into the proof of this. And it contains some of the ideas in the proof of the first theorem, but somehow in the case of these Fuchsian groups, it actually is kind of easier to finish off than the case of the Kleinian groups. Any questions so far? Okay. Okay, so I'm going to focus on one particular case, the so-called 334 triangle group, and then this 334 is I'll do it like this. So it's pi over 2, pi over 3, pi over 8. If I take 2 copies of this, so this is just, yeah, it's not that. Before 3, 3. So this 334 triangle is built from 2 copies of the 238 triangle. And in fact, once we've proven this, it's easy to the same for delta. So once we prove this one, it actually follows quite easily that the same statement about being determined by the finite quotients holds for the 238 triangle group. I mean, I say it's easy. I mean, it uses the solution to the Nielsen realization problem by Kirchhoff, but once one has that, then it's easy. Okay, so what's the plan? So there's 2 key steps. So again, just for emphasis, we have, you know, lambda finitely generated, residually finite, and C of lambda is the same as C of delta, where, you know, delta now will be delta 3, 3, 4. So the first thing is that, so on the face of it, lambda is just this finitely generated residually finite group that's kind of, you know, way out there in Scotland or somewhere. We want to kind of get some control over it. These Fuchsian groups, these are linear groups. And so what we're going to first show is that one can, in fact, build a representation of lambda into a subgroup of delta. Now, of course, we can always do that by just taking the trivial representation, and that does us no good whatsoever. But the point here is where L is actually a fairly large group. L is a non-elementary. So non-elementary, this just means, well, it suffices to take this that contains a free non-abelian subgroup. So that's the first part, that one builds this big representation of lambda onto some subgroup of delta. And then secondly, we show that if L is, and this is the kind of the easier part in this case in comparison to the previous theorem with Brightson and McReynolds and Spittler, if L is different from delta, so if this rejection goes onto a proper subgroup, then L as a finite quotient that delta does not. Of course, that's not good, because then that means that lambda, because it surjects onto L, has a finite quotient that delta does not, and that's a contradiction. So the upshot of this would be, so this would imply that in fact L is equal to delta, and then once L equals delta, we can finish. And I'll talk a little bit about this later. So the key point is first building a representation, and then secondly proving that the representation surjects onto the given triangle group. Okay, so how do we do this then? Well, as usual, we need to organize finite quotients. So, you know, that brings us to the profinite completion. And, you know, my assumption is that, you know, children in Brasilia know all about profinite completions because Pavel's there. But I'll say a few words about the profinite completion anyway. So just let's recall that it's constructed as follows. We've got our collection of all finite index normal subgroups. Let's call that script n. And then we make that into a directed set in the following way by reverse inclusion. It builds these natural epimorphisms between these finite quotients. And then we take the inverse limit of this inverse system, and that defines the profinite completion. And so we should all be proud owners of the books by Ribs and Zaleski. And so if further details are needed, then I encourage the viewer to consult that fine book. So that's the profinite completion. Maybe a slightly more concrete way to think of it is as follows, that we can, each of these groups, gamma mod n is a finite group. So we equip that with a discrete topology and it's a compact space. We then take the product over these finite groups. So that is a compact space by Tikhonov theorem. And then we can take gamma into there by just sending an element gamma to the obvious vector. And then gamma hat is just the closure of gamma in this product. And so that's another way to think of the profinite completion. And in the setting that we have, residually finite groups, this natural map that I just defined above is injective, okay? So if you're residually finite, you can't be in all finite quotients. So that means it's injective. Okay, so that organizes the finite quotients and turns gamma into gamma hat, which is a compact Hausdorff totally disconnected topological group. But on the other hand, that doesn't cheer us up very much. The power in the theory of profinite groups comes from the connection between the discrete group and its profinite completion. And we have this, and I'll just state it informally, this correspondence theorem. That kind of says the following, that there's a bijective correspondence between subgroups of finite index in gamma and open subgroups of gamma hat. And then, in fact, one can even say something even more abstract at this point. By work of Nikolov and Siegel, this open can be replaced by just finite index subgroups in the profinite completion. Nikolov. So this gives a nice correspondence between the subgroup structure of the discrete group and this, sorry, the finite index subgroup structure of the discrete group and the finite index subgroup structure of the profinite completion. And in particular, we have that in fact that, you know, C of gamma is C gamma hat. So gamma and its profinite completion are the same finite quotients. Now what's true, and again, let me just kind of say it, that, you know, C is an old result from the theory of profinite groups, but see Pavel's book with Reib's, for the proof. So we've just noticed that, you know, if these two guys are isomorphic, then they have the same finite quotient. And what needs some work is to prove that same finite quotient is actually enough to recover the profinite completion. So that turns the set of finite quotients into something more useful, namely this profinite completion that allows us to bring to bear the theories of profinite methods to study this question. And maybe it also allows us to kind of succinctly state the original question. So in the terms of profinite rigidity, so we'll say that gamma is profinitely rigid if whenever, oh, sorry, back to my old notation, whenever lambda hat is isomorphic to gamma hat, then this implies that lambda is isomorphic to gamma. So in the language that I've just introduced, so today we're just going to show delta 3, 3, 4 is profinitely rigid. Any questions? Okay, so with this notation, we can finish off. So the point is that profinite groups have the Hopf property. So if we've got G as a finitely generated profinite group, and phi from G to G, continuous epi, then phi is an iso. So given this from what we had before, so from 1 and 2 before, we deduced that we had this epimorphism from lambda that went on to delta. So we have lambda hat is isomorphic to delta hat. And we have this map that goes on to L hat, which is also delta hat. So now we've got this continuous epimorphism now. So then the Hopf property implies this is an iso. And so this implies lambda isomorphic to delta. So it's very easy once one arranges those two previous things. Let me just go back to refresh. If I can find, here we go. Yeah, first we want to build this representation back into delta and then prove that in fact it's onto delta. And then once we have that, the theory of profinite groups applies quite quickly to show that in fact they must be isomorphic. Okay, so let's first of all talk about, this is part 2. That if L is not delta, we can build a finite quotient. Now, in fact, there are various ways to finish off when we get this far. And, you know, depending on your taste, you may prefer one over the other. And today I'll do one that I think is interesting in that it provides additional information that is not so visible by some of the other methods. Okay, so let's just think about this particular L. So L is a non-elementary subgroup of delta. Now, the structure theory of these finitely generated Fuchsian groups is very, very rigidly controlled. If you're an infinite index subgroup, then you're just a free product of finite cyclics. Or if you're finite index, then you're a 2-orbifold group. So you're virtually a surface group. Now, in this case, this can't happen. Why? Well, notice that delta abelianized, if we just quickly do that, we see that that's just isomorphic to Z mod 3Z. But if you've got a free product of finite cyclics, there's no way you can have abelianization that's just simply a single copy of Z mod 3Z. Okay, if you've got some infinite cyclic factor, you get some infinite cyclic factor. And if you've got some other finite cyclic factor, then you get some other cyclic factor. So once you get to that point, it's easy in this case to rule out the existence of such a possibility. So again, the point is that, you know, let's just for emphasis here, you know, lambda surjecting onto L, okay? So the only thing that the abelianization of L could be is trivial or Z mod 3Z. But it can't be either if it's a free product of finite cyclics, non-trivial. The other case is this, that H2 mod L is a closed 2-orbifold, and I put in here with underlying space S2. So again, the point here is, so let me just draw a picture perhaps. So here we've got the upper half plane, and we take this quotient, and we get this 2-orbifold. And it has some marked points on it. So we have some cone angle. Again, it doesn't matter so much about what they are, but they correspond to elements of finite order in the fundamental, in the group. Now, whenever you have some genus, you get maps to Z. So in fact, in this case, it must just be something like this. Okay, again, the maps to Z give an infinite abelian quotient of L, which would in turn give an infinite abelian quotient of lambda, which delta cannot have. So the only thing it can be is a sphere with some marked points. But now in this case, what one can show is that if L is not a triangle group, then L and hence lambda has a PSL2 F quotient. Here F is finite, that delta 334 does not have. So you can explicitly find, in fact, infinitely many different PSL2F quotients that the L has and hence lambda, but delta cannot have. And I'll say a little bit shortly about the very strong restrictions on PSL2 representations of these triangle groups. So how does this come about? I mean, let me not say too much about this, but the magic worlds here are kind of Teichmuller theory. And really what this is saying is that if you've got a large dimensional space, i.e. bigger than or equal to 1, of characters of representations into SL2C, then you can always find one of these PSL2F quotients that the triangle group does not have. So then using this, one's reduced to the case of the L as a triangle subgroup. Of delta. And once again, it's very easy to see that there's only one such subgroup, namely delta 4, 4, 4. So this occurs as the kernel of the map to abelianization of the triangle group. But notice that L can't be that because the abelianization is certainly not going to be Z mod 3Z. So that cannot be the group L. And so therefore this implies eventually that L must be equal to delta. Okay, so this kind of mix of the Teichmuller theory together with the control that we have from before. Yeah, was that a question? Okay. This Teichmuller theory with the extra control allows us to conclude that the group L is actually equal to delta. So this is something that, you know, in kind of the program that Martin and McReynolds and Spitler and I had in our previous theorem, it was much harder to get to the end game. Here it's much easier. And in fact, there are other kind of easy proofs without the same information that we do have. Okay, let me talk a little bit about PSL2 representations of delta, because that's going to be important, not just from what went before, but what's to come. So the point is that delta has very few PSL2C representations. And in fact, I'm only really interested in infinite representations in this case. So if we think about what the representation into, I've just got matrices here, but let's not sweat the difference. So if we're looking at representations into PSL2C, then up to sign, the matrices look like this. You know, A has order 3, so we've got a cube root of unity. B has order 3, so we've got cube roots of unity again on the diagonal. And then we can always conjugate so that this Mobius transformation fixes infinity, and this Mobius transformation, the second Mobius transformation, fixes 0. But now AB has order 4. So what can the image of AB be? Well, it can have orders 1, 2, or 4. It can't have order 1 because that would kill AB, and so therefore we would just get a finite cyclic group. If AB had order 2, if image of, let's call this representation rho, if rho of AB had order 2, then what we would see here, the image is, well, it's just the triangle group 3, 3, 2, which is finite. So this is just a A4 finite group. So the image of AB has actually got to be order 4. So rho of AB to the 4th is 1. Well, what does that mean? Well, if we look at the trace of rho of AB, so that's equal to omega squared plus r plus 1 over omega squared, which is omega plus 1 over omega all squared minus 2 plus r. Now, omega plus 1 over omega, that's, so omega is a cube root of unity. So this is plus or minus 1. So that's equal to 1 minus 2 plus r, which is equal to 1 plus r. Now, the image of AB has order 4. So what's the trace of an element of order 4? Again, in PSL2, this is just plus or minus root 2. So here we see then that we conclude that r is just minus 1 plus or minus root 2. So we've got 2 representations into PSL2C with infinite image up to conjugacy. One's in SL2R and one's in SU2. I forget which is which, but that's kind of the picture. So the representations into PSL2C are very rigid. They just look like one or the other. Okay, so that's why back here, it was easy to kind of build PSL2F quotients that the triangle group didn't have, because in fact, the above argument, so this argument, you know, works for FP bar as well as C. So if we took an algebraic closure of the field of P elements and run the same argument, well, you get a similar kind of argument. You just see these 2 representations. Well, okay. So similar argument, similar outcome, i.e. Now, maybe in some cases, these reps themselves are conjugates, so they're actually less than 2 representations into PSL2 FP bar. But the point is that, you know, there's at most 2 again using this argument. So this is kind of saying that the PSL2F quotients, the finite PSL2F quotients that you see, are very restrictive. Okay, they're just given by this. Okay, so what's the point now? So we're going to use this in a particular way. So the magic words here is Galwa rigidity. So if we go back to this representation here, So what we see is that the traces, if we look at the trace of rho of delta, where we take either of those two representations, so the trace of this lives in z root 2, which is the ring of integers of q adjoin root 2. So we have exactly these two representations that come essentially from number theory, since this field extension has got degree 2. And that's what Galwa rigidity is really telling us, that, you know, when we have these groups, let me be a little bit informed, we've got gamma inside SL2K, where K is a number field, i.e. a finite extension of Q. Then if you take an embedding from K into the complex numbers, this gives a representation. So rho sigma that takes gamma into SL2, well, you apply the Galwa automorphism. So whenever you've got this group that lives in a number field, you can build Galwa conjugate representations. And what Galwa rigidity is saying is that that's all the representations that you can see. So Galwa rigidity means that all sort of interesting, let's say irreducible reps come from number theory, come from the, let's see, come from the trace field. Okay, so in these previous cases, when you had this deformation space, you can vary the trace field and get lots of finite quotients that you can't if you have this property. So Galwa rigidity is a strong property. I mean, even amongst triangle groups, not every triangle group is Galwa rigid. I mean, every triangle group has zero-dimensional SL2C character variety because they have property FA, but not all of them have this even stronger property. And so it's been somewhat prohibitive in getting examples. You really need a mix of happy circumstances to find collections of groups for which you can apply the Galwa rigidity in a way that can also be coupled with an endgame. Okay, so let me just say a little bit now about how to build a representation. So here we've got lambda hat isomorphic to delta hat. So as we've seen, the traces of the group delta live in the ring Z adjoin root 2. So in fact, what's true is that, you know, delta is an arithmetic Fuchsian group. And without getting into the details of this, I mean, so this means that delta arises, and let me just put it like this, from a quaternion algebra B over Q root 2. So in fact, in this diagram here, what we really should think of is that we use this quaternion algebra. If we look at B1, this quaternion algebra, it embeds inside SL2K. Delta is living inside there. And then by taking completions of this algebra at various prime ideals of Q root 2, this gives the representation that goes into SL2 QP bar. And then just formally SL2 QP bar embeds in the complex numbers. And so SL2 QP bar embeds inside SL2C. So for each of these representations, for each prime of this number field, we get kind of a representation that lands up inside SL2 QP bar. Now, what's important here is that because the traces, we had the traces of delta contained inside Z root 2, so that the image here of these representations is an abounded subgroup. So in fact, it goes inside a bounded subgroup of SL2 QP bar. And so this means that we've got a representation then on the profinite completion into that bounded subgroup that induces a representation on lambda hat that then gives a representation from lambda into SL2 of QP bar for every prime P. And then the crucial thing is that one is able to use the fact that the group is Galwa rigid to patch together these representations to say that the only possible thing that lambda can do under this representation is do the same as delta. It lands up inside this quaternion algebra B. So there's a little bit more to say there, but I don't think it's worth me spending any time. This is the key idea here in this kind of representation rigidity part that uses the Galwa rigidity to control representations of lambda and force it, again, with some additional control that the properties of this quaternion algebra that I'm also sweeping under the carpet that fails for 237. Okay, but I think time is almost out, so let me just finish up. So as I said, it fails for 237. And the reason it fails is kind of at the last part where all we can conclude is either in the notation that I said before, that we get L back inside delta 237. And that's a win. We can run the argument as we did before. Or the bad news is that L is contained inside PSL2 O, where O is the ring of integers of the field Q cos 5 or 7. So the problem here is we're essentially only using what might one consider congruence quotients of the triangle group. And in the case that we considered, the congruence quotients are different from the congruence quotients of PSL2 Z root 2. Unfortunately, in this case, they're not different from the congruence quotients of PSL2O. So we can't distinguish these two guys by their congruence quotients. And infinite index subgroups of these groups are, really poorly understood. And so that's why one can't make progress. And indeed, perhaps to finish, one can't really make progress even on a group that one might make progress on. And in fact, even going back many years, Lobotski had tried to prove that SL through Z was profinitely rigid, but couldn't. And the problem becomes that one can build the representation as before, and even gets a one-to-one homomorphism from lambda back into SL3Z. But one again doesn't know enough about finitely generated subgroups of SL3Z to conclude anything useful. And so with that, I'll stop there. Muito obrigado.
Let's thank again Reid. Please switch the microphone. Now it's time to questions. Mm-hmm. Somebody have some questions, comments, and so on?
Well, I have two questions actually. First question, well, this triangle groups that you can prove that they are profinitely rigid, right? Of course, you can make a free product of them and they will continue to be profinitely rigid.
I don't know.
Well, I think, well, for these groups, I'm sure, but I almost sure that it is not so difficult to prove, but because they're generated by torsion. But you have many other examples that you proved before profinitely rigid. So actually my question was whether it is clear for you for which groups this is the case and for which group it is not.
You mean profinitely rigid?
Yeah, you have many examples that you proved before that they are profinitely rigid.
Yeah,
also.
Yeah. Many is still finite though. I mean, we do know infinitely many examples of groups that are profinitely rigid, but
and
this comes from taking like the fundamental group of the Weeks manifold and direct summing with some number of copies.
Of course, you can take two groups which are profinitely rigid that you know to be profinitely rigid and make free product of them, right? And I'm sure that in this case that you were consider that it should be the case.
Right.
That it should be
so why is that? I mean, that's not always true, right?
No, it is not. Well, it is not always known, I would say,
Yeah,
because
right.
very messy of question. You can make free product of that, of course.
Right, exactly.
All right, but here your groups are generated by torsion. All right, and this make it easier.
I see, but you must be still using something else, because you could take finite cyclic group and free product with a finite cyclic group. I don't think we know those are profinitely rigid.
If we have finite cyclic groups, well, I think they should be. I mean,
well, they should be, but I don't know if it's known to be the case. That's what I'm saying.
Right. Well, I mean, in this case, I'm sure that they are.
Okay.
Right.
I'll
but
take your word for it.
You have actually more complicated groups, right? And so my question was about this, but I mean, and my second question was if we have different Bianchi groups, right? So within this world, right? Can we prove that if they have the same profinite completion, then it is the same Bianchi group?
Just amongst Bianchi groups.
Yeah. I mean, we take two different Bianchi groups and make a profinite completion, and suppose we got the same group, right?
Right.
Is it the same Bianchi group then?
Yeah, the answer is clearly going to be yes, but I don't know how to prove it right now. I mean, you can get it down to there's only finitely many, just using sort of class number considerations. But to rule it out might be a little delicate. I mean, maybe some analysis of, the finite conjugacy classes of finite subgroups might do it, actually. So conjugacy separability of the Bianchi groups, I think, is known by certain people's theorems, if I recall correctly.
Yes.
Okay, so then probably, any finite subgroup of the profinite completion then is kind of conjugate to one of the finite subgroups in the Bianchi group.
Yes.
And then
that's what I want to use in the previous question as well.
Aha. Yeah, but in the previous question, anyway, but for the Bianchi group, then I think possibly you just have to understand the finite subgroups of the Bianchi groups, but that gets quite complicated as the discriminant of the field gets large. I mean, there's only finitely many possible finite subgroups in the Bianchi groups. It's the way that they're kind of arranged that makes it complicated. But let me think about that and get back to you, Pavel. I mean, there must be some chance that one could be able to do that.
I was thinking maybe, I mean, you split it in an amalgamated product or each an extension, and you have certain hierarchy there.
Yeah, but you see, as far as I know, you could have the same profinite completion as something that splits as a free product with amalgamation, and it need not be a free product with amalgamation. So I'm not sure the hierarchy.
Yeah, they split over separable group, and in this case it is.
Right, but groups can have lots of different hierarchies, I guess.
Yeah, that's true. Even limit groups.
Right. But yeah, let me think about that. I can't finish it off whilst I sit here.
Some other questions, comments?
Yeah, I would like to ask a question.
Yeah,
if I understood you well, so this Galwa rigidity is the same as zero dimension of character variety?
It's not quite the same. It's more. It's stronger than that in some sense, because all triangle groups have got zero-dimensional character varieties, SL2C character varieties.
Really?
There.
Okay.
But some of these triangle groups don't have Galwa rigidity. So, for example,
Galwa rigidity is that there is one Galwa orbit.
That's right. Exactly.
Okay, I see.
So something like, if you take the triangle group, delta 666, that doesn't have Galwa rigidity because it admits an epimorphism onto the 662 hyperbolic triangle group.
I see. Okay, I see the difference now.
Yeah. No, we've been working hard to try to tweak this, and there might be other ways of getting around Galwa rigidity, and actually just, you know, use zero-dimensional character variety might be enough to make progress. But that's where we are.
More other questions?
I have a question.
Hey.
Professor Reid, given that we're distinguishing the triangle groups by quotients in algebraic groups over finite fields, is there hope that they might be distinguished between, by their P completion for some finite set of primes instead of the full profinite completion?
Well, they don't have, I mean, virtually they have interesting pro-P completions for all primes P, but they only have very restricted pro-P completions for a list of P because the abelianizations are all finite. And so I'm not sure that the pro-P completions would be enough to do it.
But if we take a finite set of primes, say a pi, and we complete with respect to this finite set of primes, not necessarily one.
No, but I think, you know, my point is that, you know, for most of the primes, you'll have no interesting completion. You'll only have anything interesting when you know, the prime divides the order of abelianization. And so, you know, for example, for the 337, there probably isn't going to be any interesting completion that would be useful.
Okay, I see. Thank you.
Yeah, sorry.
More other questions? If not, let's thank again Reid, please.